I took the podcast on the road to the first robotics competition. This incredible organization brings together a vibrant community of kids ages 4 to 18, fostering their passion for science and technology through team-based robotics programming. On this episode of Forging the Future, I had a chance to talk with Dave Lavery, Program Executive for Solar System Exploration at NASA. Let's check it out. Welcome to Forging the Future, and we're here today at the first World Championships with Dave Lavery, the Program Executive for Solar System Exploration at NASA. Now that sounds like a cool job.
It is, quite a bit.
I want to get one of those cool shirts. Is that NASA issue there?
This is official NASA issue as one of the Space Station Expedition crew shirts.
Really?
Yes.
Okay. I have to go get down to Space Center Houston and see if I can pick me up one of those. So you're responsible for the management of the design and development of the next generation of Mars exploration. Now that sounds like a pretty tall task. Yeah.
It is, but it's been an amazing time over the years working with the Mars exploration program, and I'm also now branching out into other areas of planetary exploration with one of the missions I'm working on. They'll be heading to Europa at the end of next year.
Oh, wow.
But the primary focus of what we've been doing in the program is really taking a look at how we want to explore the planets, specifically in this case, how we want to explore Mars and what sort of machines it will take to do it. Eventually, we will be doing it with humans, but for right now, the only way we can do it is robotically. So what sort of robots do you need to be able to cross the surface of Mars safely, robustly, and over long periods of time to conduct the sort of scientific exploration that we want to do? Mm-hmm. And then from that, once you have the basic answer of what you want to do, then you've got to figure out, how do I actually build the machine that can do that?
Yeah. Well, how long have you been doing that for NASA now?
So this has actually been the majority of my career. I've actually been with NASA, if I include the time early in my career when I was there as a contractor, then later switching over to being a civil servant. I've actually been around the program for about 4 decades now, and have been able to see a lot of advancement, a lot of maturity in the technology and the program itself, and had a pretty amazing experience all the way through while I've been doing it.
So you founded something called the NASA Robotics Alliance project, and that has also some participation with FIRST. Tell me a little bit about that.
So about 28 years ago, at the time I was running the robotics technology program for NASA, and we were responsible specifically for creating the new technologies that would be incorporated into rovers for planetary surfaces, but also looking at in-space robotic systems, free-flying robots. And as we were going through our annual program to look at what new technologies would be created, we started to notice that the people who were bringing these ideas to us were basically the same faces over and over and over. And each year they were getting just a little bit older and a little bit grayer, and there was nobody in line behind them. And we started to realize we had a growing problem of having in-house robotics expertise to build the next generation of planetary explorers. And about that time, actually kind of by accident, we stumbled across FIRST. A couple of kids in my neighborhood actually had seen a very short piece on an evening news program about the program, came down the street, talked to me, talked to my neighbor who also worked with NASA Robotics Systems, and asked both of us, hey, we saw this thing about this robot program. You guys work with robots. Would you help us do this? And purely because we didn't know any better, we signed on and said, sure, we'll give it a shot and see if we can help you, with the idea that we were just helping some high school kids. Once I got involved and saw what the program was really doing, instantly recognized this pipeline problem that we were concerned about with not having anybody coming up as the next generation of robotics experts for us. This is where those future employees would come from. Programs like this that were getting students excited about engineering and math and really inspiring them to consider engineering careers as something beyond their academic careers were exactly the sort of resources that we needed to tap into to say, this is where my next generation of robotics experts or rover builders or free-flying robotic system creators, this is where they were going to be.
Yeah. And now it's not just a theory, right?
Absolutely.
I was talking to a gentleman in the NASA booth right over there or downstairs, and he was telling me he started out at first and went through the program, and now he's working on a rover at NASA that's going to be drilling into the the south pole of the moon,
Right.
looking for water. And so if you think about the different leagues here, starting at Lego League and the First Deck Challenge and FRC, and it's like the next one is doing stuff that you're doing, which is trying to figure out how to move a robot on a planet that's 8 months away, right? So you're doing the Mars rover, right?
Yep.
And the helicopter, right? So I mean,
And that's exactly why we put what we created was this thing that we now call the Robotics Alliance project.
okay.
Whereas basically to help us help participate in programs like FIRST that would let us talk to the students that were participating, get to know them, understand them, and see, are these the sort of folks that we can basically recruit to come in and work for us? And as a result, this project that we put in place has now put a well-integrated structure across NASA in place that allows us to broadly look at the students that are populating the teams and bring them in-house where we can. And as a result of that activity, over the course of the last now 25 years that it's been in existence, we have former students, now alums, now NASA employees who are working on projects like Viper that will send a rover to the south pole of the moon. Or in other cases, we have the Ingenuity Helicopter on Mars that right now is being led by Teddy Zanetos and Josh Anderson, who are both FIRST alum.
Wow.
And so we find now a lot of different projects where FIRST alumni have become very well infused and integrated and are now leading those efforts, in large part utilizing some of the same skills and abilities and talents and knowledge that they gathered and learned while they were on their FIRST teams.
And trying to get a rover landed on Mars. And originally it was only supposed to last like 90 days, right? And how long has it been going now?
Well, so over the course of this series of rovers that we put down on the surface of Mars, every single one of them has gone on to last a lot longer than their original design prime mission. For example, the very first one, the Sojourner rover back in 1997, was originally just supposed to go on for something on the order of a week and drive about 10 meters. It ended up actually lasting 93 days and going on for well over 100 meters of travel. And then we've gone many, many times beyond that. Spirit and Opportunity from January 2004, they were supposed to last for 90 days each. Lasted, in the case of Spirit, over a decade. And Opportunity lasted 17 years before it finally ended its mission. And the Curiosity rover that is there since 2012 was going to be a 2-year mission. We're now more than a decade later. It's still going strong. Perseverance that is there now, again, was going to be a 2-year mission. Now we've sort of redefined its mission with the expectation that it'll still be going by the end of this decade, when the samples that it is collecting right now are actually going to be gathered up and put on board a return craft that will actually take those samples and bring them all the way back to Earth.
Oh, wow.
So these missions are going on well beyond their prime missions because they tend to be engineered and designed so well that they are able to surpass their original design goals by a fairly significant factor.
And you also built one of the first flying robots for Mars, right? And tell me a little bit about that project, as I imagine that would be particularly challenging when nothing's ever flown on Mars before, right?
Yeah, so the Ingenuity Helicopter is the first aircraft that's ever operated beyond Earth. And it's the first time we've ever had to really look and utilize aerodynamic effects and aerodynamic propulsion as a way to actually move around and navigate on another planetary surface. And in this case, we chose the helicopter as the basic design form for a number of different reasons. But the first thing we want to do is just, more than anything else, this was built as a technology demonstrator. All we wanted to show was that atmospheric aerodynamic flight was possible on another planet, and then begin to sort of push the envelope of how well the technology might work. Were there things about the dynamics in the atmosphere of Mars that were substantially different than what we would have on Earth? were the things that would be surprises, stuff that we didn't even know to ask, and that we would learn as a result of flying around the atmosphere of Mars. And those are the sort of things that we were after. The original plan, similar to the case with the rovers, the original plan was just demonstrating, yes, we can fly and do controlled flight, would be done over the span of 3 to 5 flights that would be done within a very short 30-day period. The helicopter was actually carried to Mars, tucked underneath the belly of the Perseverance rover. The Perseverance was basically going to drop us off, help us act as a communications relay between the helicopter and Earth for about 30 days, and then we'd end that activity and the rover would drive off and the helicopter would stay where it was on Mars, and the rover would then continue to do its primary mission over the next 2 years. What ended up happening was we obviously were able to demonstrate that, yes, we can fly on Mars, but it actually turned out that we were able to fly with enough control authority that we felt very confident that we actually could extend beyond that first set of 5 flights. And we were able to transition from just a technology demonstration to validate that, yes, flight's possible. Yes, we understand how airfoils work in the very, very thin Mars atmosphere. But now we can actually demonstrate, doing what's called an operations demonstration of, now let's utilize the helicopter to see, can it actually do tasks that are beneficial to the rover operations? Can we act as a scout? Can we actually conduct a scientific data gathering about the atmospheric properties of Mars? Do things like that extend and add to its original purpose. And that's what the helicopter is doing now. As of this past weekend, we've just flown the 50th time with the helicopter. It's flown on the order of 10 kilometers of total flight distance, and it has total flight time of several hours versus the very few seconds that we thought we were originally going to get with a helicopter. So it also, what it's doing right now is, again, sort of going in and flying over areas that the rover either can't or doesn't have time to go and explore, returning images from there that then get passed to the science team. We have been able to do things like, there's a microphone on board the rover. We've been able to fly near enough to the rover so that we've actually been able to hear the helicopter in flight. Now, that's interesting and kind of neat, but it also serves a scientific purpose because we can look at the acoustic shift associated with a helicopter in flight, and from that extract certain properties about the density, the dust loading in the atmosphere, the speed of sound in the atmosphere on Mars, things like that. All of that is of significant interest to the Mars science community. One of the properties that we have to contend with to make the helicopter work is the fact that the atmosphere on Mars is very, very thin. It's about 1% of the atmospheric density of here on Earth. So it's about
really
equivalent.
Only 1%? Wow.
Yeah. So it's about equivalent to trying to fly a helicopter at 100,000 feet on Earth, which is way beyond the typical flight envelope of helicopters.
Did you try to do that, or how did you test something like that?
So what we end up doing, the thing that acts in our advantage is, although the atmosphere is very thin and so it's very, very hard to generate lift, the thing that does act to our advantage is the fact that Mars gravity is only about 1/3 that of Earth. So we only have to generate 1/3 of the lift that we'd need here on Earth. So how do you test that and actually show that the system is going to work before you launch? Well, we've got test chambers at the Jet Propulsion Lab in California that we can basically pump down to Mars atmospheric pressure and simulate the atmosphere environment on Mars. And so we took the helicopter, put it inside of there, and just tested the heck out of it to make sure we could do it. But then the one problem is, okay, you get the right atmospheric pressure, but how do you compensate for the fact that gravity is not the same? And so we actually built a gravity offset system that could lift basically 2/3 of the mass of the helicopter. So it only had to lift the remaining 1/3. So it had to, in effect, put out the same level of effort that it would have to on Mars. And you test it in that condition to see how well it would work.
When it flies, is it autonomous? Because there's also a communication delay, right? So it's not like you've got a remote control and you're trying to fly the helicopter.
It's
right?
It's actually completely autonomous and self-contained. It actually was a case where in that very low atmospheric pressure environment, trying to control it as a human, you just can't react fast enough. When we did try to have a human control it, it crashed almost instantly, just about every time.
Like those small drones they used to sell.
Yeah.
Right? You could not control
You
those
just can't
things.
control them.
Yeah.
But when we had the autonomous control system on board that could react faster, we were able to get and maintain stable flight. In the case of the helicopter, now that it's on Mars, the reason we had to do that is because the round-trip light speed delay for the communication signals can be anywhere between 11 and 40 minutes. And so you can't sit there and joystick at real time. It just is not going to
No.
work. And so instead what we do is about twice a day we have an opportunity to talk to the helicopter, where we send a signal up to Mars, gets relayed down and stored aboard the rover, and then the rover acts as a communications relay, forwarding then the communications onto the helicopter, and then the reverse happens. And like I said, about twice a day we can talk to the helicopter. Once a day is our typical pattern, where we'll basically, when the helicopter wakes up in the morning, we'll give its command load for the day and tell it what we want it to do. And then it has enough embedded intelligence on board to then go and conduct the flight operation that it needs to do, fly where we command it, go in and land autonomously, send the signals back, which then get relayed back to Earth later on in the evening.
How far away can the helicopter get from the rovers?
So we typically, the communications link between the helicopter and the rover is good if things are unobstructed in terms of direct line of sight, out to about 1 kilometer.
Okay.
In practice, most of the time we tend to stay within about 0.5 kilometer, and that whole distance gets shortened if there are intervening hills or terrain that might occlude the signal, things like that.
And then what about the processor on the helicopter? I mean, what kind of smarts does that have? I know the Apollo mission had about the equivalent of a TI calculator or something like that, which is amazing. But what are you putting on these rovers nowadays? So
the processor that's actually used on board the helicopter right now is the same as a commercial version of a Snapdragon processor like you would have in your cell phone.
Mm-hmm. Okay.
And so it's that sort of capability, which in one sense seems like it may not be a whole lot, but in terms of space qualified processors is actually a considerable leap ahead beyond standard practice.
Mm-hmm. Now you're working a lot with new technology, and when I was down at IBM at FSD, it was during the shuttle days, right? And the challenge there was all of this space qualified hardware was like 20 years old or 15 years old. I mean, the displays were like monochrome vector-based displays, and this is at the time when the PC was first coming out and everything. I mean, how do you address that part? Because you're trying to be ahead of the curve, right? So,
well, in most cases, if you take a typical spacecraft and you take a look, for example, at the computing power on board, it would appear that it's several generations behind what I'm going to have on my desktop or even in my cell phone. Mm-hmm. And that is because the typical case where a space-qualified processor is always a special variant of the sort of computers that we have on the ground. It goes through, in particular, radiation hardening and redesign work, and the process to qualify a processor for space is long, involved, and very expensive. So it's done on a very irregular basis, and it tends to lag a generation or two behind, at least, behind what you may have on your desktop. Mm-hmm. The interesting part about the helicopter project, though, because this was a technology experiment, it wasn't a full-up operational science system like the rover is, but the helicopter as a technology experiment meant that we could use, in effect, non-standard non-space qualified parts. Mm-hmm. We are using commercial-grade parts several different places on board the helicopter. And we're able, as a result of that, to use stuff that is, in the terrestrial context, more current, provides more processing power, but the other side of that coin is it's also riskier because it is unproven in a space environment. It is more susceptible, for example, to a radiation hit than a space-qualified processor might be. But because we thought this was going to be a very, very short mission, it was, in the overall risk balance, worth it to try to do that. And so we've been able to, as a technology experiment, take advantage of more mature technologies here on Earth that might not otherwise be ready to fly for maybe another 5 or 6 years.
Because it's experimental, essentially.
Exactly.
Yeah, I suppose in one scenario, everyone was hoping, okay, it might take 3 flights and fall over, and then, okay, oh well, that's it. I mean, but there's still a lot to learn in some of those early missions.
Exactly.
But great that you're able to do it.
Yeah.
I mean, how do you over-engineer something? It seems like you guys are onto something where it's these rovers and satellites last so much longer than you thought they would, right?
Well, a lot of the performance that we've seen out of these systems are designed around the way we specify the problem in the first place. For example, let me talk about the Spirit and Opportunity rovers that landed in 2004 and then went on for a decade and 17 years. Their prime mission was 90 sol is a Martian day, slightly longer than an Earth day. It was 90 sols longer. But we had to design the system so that we could pretty much guarantee that it was going to be able to last that 90 sols with on the order of 98 or 99% confidence that it would be able to survive the Martian environment that long. And the Martian environment is one where, for example, in the worst parts of winter at midnight, you can see temperatures of 150 degrees below zero. And so you have to be able to survive that sort of cold soaking and constant thermal cycling. And to be able to be able to guarantee that you can survive for at least 90 days in that sort of an environment, the engineering required for that is so rigorous and so difficult that the difference between lasting 90 sols and 4,000 sols is very, very small because you've already sort of proven you can survive. Typically what is going to happen is either you're going to have the system fail sometime in the first couple of days, something is going to break because it can't survive the environment, or if it can survive past the first couple of days, you're probably going to be good for a very, very long time. In our case, we wanted to be sure we would be good for at least 90. Once we were there, then going from 90 to a couple of thousand didn't require any change in the design or the engineering. It was just the exposure and how long we would last in the environment.
Right. It seems like there's been a shift in NASA's approach toward, this deep space and exploration, at least over the last 35 years since I was at NASA. I mean, what's behind that, from your opinion, or is there a change in motivation or change of focus? Or
I think the biggest thing that has impacted us in terms of the types of missions and the frequency of missions is the relative increase in accessibility, that we're now able to fly more missions more frequently than we could 10, 20, 30 years ago. And as the commercial launch community has started to build up an increase, and as a result they're building more launch vehicles, that has given us more opportunities to be able to say, hey, we can grab one of those and start doing more frequent missions to Mars. Now we're doing them approximately every 2 years, which is the launch opportunity period, that we're able to fly at almost every opportunity, whereas 20 years ago that was not the case.
Yeah, getting a rocket off the ground back then, like Apollo, etc., billions of dollars, right? Now you can put it on a Falcon rocket and get it up there or whatever commercial platform, and then do stuff remotely, right? I mean, just like what you're doing. You don't have to get a person there, which makes it much, much more complicated. So
yeah, the sort of advances we've had in the technology, specifically in robotics and artificial intelligence technologies over the past couple of decades, that allow us to do remote operations and put more and more capability on board the spacecraft so that we can act more as supervisors of the spacecraft operations rather than every turn of a motor or every movement of a joint or every sample acquisition or data acquisition being commanded directly with human intervention. Instead, we give high-level commands to the spacecraft and tell it what we want to accomplish and let it do all the determination of how to make that actually happen. And that's been a real boost in terms of spacecraft operations, scientific operations, and data collection.
Interesting. Well, you've been a mentor here for 25 years at first. Maybe a little bit about what that's been like for you. Why do you do that?
Well, as I mentioned, our original involvement was to help us identify students who could come into the NASA aerospace community, specifically the robotics community,
Right.
and start working with us to develop the next generation of systems. Over the past almost, and now actually going closer to 30 years, this is my 28th year of mentoring a team directly. Over that time period, we have definitely had that happen and been successful at bringing in a lot of students that have started getting to know us through their ability to work with us on some of the first teams and some of the other programs that we worked with. And so we definitely have seen that success. And for me, as a team mentor, being able to take some of the students that I've worked with directly and watch where they've gone in their careers, where they have come in some cases into NASA and worked on some of our systems. One of my students worked, for example, on the Curiosity rover directly while he was at the Jet Propulsion Lab, as well as seeing where they're going elsewhere in the aerospace community as an industry has been wonderful, because that means that part of it is working. But the other part of it as well that people may not instantly see, that I think is also just as important, and I realize this as a mentor on the team as well, is our goal is not to turn every single student into an engineer. That wouldn't be any better than if we said we're trying to turn them all into lawyers, or trying to turn them all into chefs, or trying to turn them all into bus drivers. That we don't want them all to become the same thing. What we do want is to educate them so that they can be smart shoppers about the academic and then eventually the professional career that they want to pick. We want to work with them so they have a chance to understand this is what the engineering profession is like. This is how a scientist works. This is how a mathematician problem solves. So then when they consider, what do I actually want to do? Well, I know a little bit about mechanical engineering. I've seen people, I've worked with the people who do that. I've done a little bit of it. That is what I want to do because I have the experience. Or, just as important, I've done it, I've tried it, that's not for me, and it's a whole lot better that I figure that out now as a high school student or a college student than doing it for 10 years and suddenly after a decade realizing I'm in a career that I'm not enjoying. So again, our goal is not to turn them all into engineers. We absolutely hope that some of them do get turned on and inspired by it. Our hope is to help them discover what they really resonate with, whether it be engineering or journalism or management or accounting or whatever, all the different aspects of these projects that they get to experience. Our goal is to give them a taste of it so they can understand it and then can use that knowledge to figure out where to go next.
And that's very powerful. I mean, with these larger teams and the different roles that they take, and they get to try on different hats, and like you said, what do they like, what do they don't like? And I've just seen so much confidence in all these kids going all the way down to grade school.
Yeah.
And so very inspiring. Well, thanks for coming on the show. Thanks for being a mentor for the past 25 or 30 years. Super interesting. Definitely be following along as you explore Mars a little further. So thanks, Dave.
Appreciate it. Thank you very much.